phone since it's already started. Hang on just one moment. Okie dokie. All right, so today we're going to talk about Chapter 2, Molecules of Life. This is basically a sort of an introduction to chemistry. So let's get moving. All right, so first, again, I apologize for the slides running off the side of the screen. I've got my picture set up a little bit differently today, so hopefully I can do some drawing on the board and it'll be a little more beneficial than previous. Again, this is a learning experience. I'm going to get better. I'm going to try to talk less with my hands today and do more pointing. But a fear of frying. Human beings have eaten foods fried for thousands of years. And it was determined in the 1950s, 60s, and 70s that frying food probably wasn't the best way to prepare it. Frying foods was associated with things like coronary artery disease, liver disease, some kidney ailments, all sorts of things. So it was determined that frying wasn't the best. In the 1950s and 60s, something called trans fats were invented, and these were hopefully at the time, it was thought that these would be better for us than the old traditional animal fats, which are primarily saturated fats. But we now know that eating trans fats actually increases the risk of atherosclerosis, which is what used to be called hardening of the arteries, and you have heart attack and diabetes. The way we make trans fats, and we'll show, I've got a slide here in a few minutes that'll show you what a trans fat actually looks like. And these are where we take an existing fat that is made by vegetables, which are unsaturated fats, and we add hydrogen to them so they would act more like saturated fat. We start off with the atom when we talk about chemistry. All elements are made up of atoms. Atoms are the building blocks of life. Life's unique characteristics start with the atoms. The reason certain organisms or certain entities like water, certain compounds, that's a better word, act the way they act is because of the atoms that are there, the way those atoms. So if atoms have certain characteristics, then you make compounds from those atoms, and then those compounds may share some of those same characteristics. Atoms consist of three parts, and if you advance in your scientific instruction later on, you'll learn that there's actually more than three. But we're only concerned about three. They're the three that humans have known about for the longest amount of time. And they are the proton, the neutron, and the electron. We'll talk about each one of those individually in just a moment. But all atoms in their normal, again, I don't like that word, it's the best one I can think of at the moment, in their normal state have zero electrical charge. They are electrically neutral. And we'll talk about why that is in just a minute. But it is the electrical properties of some of the subatomic particles that make the atoms do the things they do. The electron is a negatively charged particle. These are found in orbitals, little shells that appear around the nucleus. The proton is a positively charged particle, and the neutron is a neutrally charged. It has no electrical charge. The protons and electrons have a ratio or an association, which we'll talk about in just a moment. And then the neutrons, the numbers of neutrons can vary greatly among the different elements. That's just a little pictorial demonstration of what an atom would look like. The green and the gray here with the plus, that's the proton, which is positively charged, the neutron, which has no charge at all, it's neutral, and then the electrons, which are found around the nucleus, have the negative charge. The atomic number, when you look at a periodic chart, there's one on the wall over here, there's one in your textbook, you can look up on the organism or the element will be given an atomic number. that atomic number is going to be equal to the number of protons in the nucleus. So anytime you're told that the atomic number of element X is 57, then you know that there's 57 protons in that particular nucleus. By extension, if an atom in its natural state is always going to be electrically neutral, then for every proton, there has to be an electron. So if element X, again, has 57 protons because its atomic number is 57, then we, by extension, know that there's also going to be 57 electrons, because to balance those 57 protons, there would have to be 57 electrons. If you need to know how many neutrons there are in a particular element, you look at its atomic mass. The mass number is formulated, or calculated, better word, by taking the number of protons and the number of neutrons found in the nucleus. This is just a simple calculation. Marker, here we go. This is a simple calculation where you have the mass number is equal to the protons plus the neutrons. If you know that our mystery element X has 57 protons, we plug that in right there, we know its mass number is 167. Then we just simply do a little bit of very simple math. So the number of neutrons is equal to the 167, which is the mass number, minus 57, which is the atomic number, and we find out that N is equal to 110. Yeah, that's a really big number, but that's what it would be. That's the way you would calculate. Normally, the number is not going to be that different, but again, this is a mystery element that doesn't actually exist. It's one I just made up. An element is a pure substance that consists of atoms of only one type. All the atoms in an element will have the same number of protons. Gold, for instance, is an element. Oxygen is an element. Tin is an element. All of those things are elements. They're made up of atoms that all have the same numbers of protons. Now, when it comes to neutron number, here, all atoms of a particular element may not necessarily have the same number of neutrons. There are things called isotopes. Isotopes are elements or atoms of elements that have differing numbers of neutrons. That's why when you look at the periodic chart, for instance, you look at the periodic table and you look up oxygen. And you and it has a atomic mass, as I recall, of 15.9994. May accidentally be another 9 in there, I don't remember, and that one over there on the wall is too far away for me to see, but for our purposes today, this is fine. So, you see, this is not a whole number. Therefore, if you did the first simple calculation I told you, then you would come up with the fact that there must be, well, 7.9994 neutrons, and that's a partial neutron. How does that work? Well, the reason that works is because oxygen has various isotopes. And again, this is not a chemistry class, so we're not going to deal with a whole lot of different isotopes. But we say there's oxygen 16, there's oxygen 15, and there's oxygen 14. That's 3 I just made up. Whether those are correct or not, I don't know. Again, not a chemistry class. But what this tells us is that this is the atomic mass of that particular isotope. So if I ask you how many neutrons are in a single atom of oxygen 16, that's where you would do your simple little calculation. 16 is equal to 8 plus neutrons. Neutrons then is equal to 8. And you could do the same thing for oxygen 15 and the same thing for oxygen 14. All oxygen isotopes are going to have the same numbers of protons and electrons, but they're going to have a different number of neutrons. A radioisotope is an isotope of an element that has an unstable nucleus. The nucleus actually will break apart and pieces of it can come off. And this happens at a very predictable rate. We know that certain elements have these radioisotopes, and we know that those isotopes are going to break down at a predictable rate. That's how aging is done. If you've ever seen a TV show or anything, and it talks about the fact that some fossil was 3.7 million years old, and that was determined by carbon dating. The way that works is we take, or we, not we, but somebody in a lab takes the carbon-14, they analyze the amount of carbon-14 that's in that fossil. We know that a certain amount of carbon-14 is laid down when living things live. So I'm alive, I'm laying down a certain amount of carbon-14. After I pass away and I'm put in a grave somewhere, 1,000 years from now, somebody might dig me up, take a sample of my living tissue that's left, bone more than likely, and then they can analyze the amount of carbon-14 that's left based on the amount of carbon-14 that has gone away or that has degraded or eroded. Then that technician could then determine that there's been that many years that has passed since I passed away. Carbon dating is relatively reliable. Again, the big thing with carbon dating is to do proper carbon dating, you have to have what was once living tissue. You can't carbon date rock, for instance, but you can carbon date a bone or some other thing. So radioactive decay is the process where these radioisotopes are emitting energy as their subatomic particles in the nucleus disintegrate. The most, reasonably well-known radioactive material is uranium. Uranium is used in nuclear fission. It's used in nuclear medicine. It's used in all sorts of places. But it is, again, a radioactive process. We can also in medicine use what are called radioactive tracers or radioisotope tracers. When my father had a heart attack in 1978, I believe it was 78 or 79, they did a radioactive isotope tracer test. What they did was they put a dye in his arm, in one of the veins in his arm, and that dye had a radioactive tracer. They could then look at him with full heart. There were 3 places on his heart where the dye stopped moving, and that told the doctors that's where his heart coronary arteries were blocked. And they, cracked his chest open, went in and did 3 bypasses to bypass those blockages. But that was the use of a radioactive tracer. This next slide is actually a picture, and you can't see it very well on the screen. Again, these PowerPoints are available to you from your textbook manufacturer. You can look at them to get a better look. But basically what you're showing here, and you can see this detail, this is the radioactive tracers of a smoker, and this is a non-smoker. When people think about smoking, they think about lung damage. Well, here's the lungs of this person. This is their liver. This is kidneys. That's the brain. That's the heart. But if you look at this image over here, you see the kidneys appear quite dull to here. You don't see the liver at all. You see very little of the lungs, and the brain looks fairly static as well. So smoking does more damage than just to your lungs. You can look at this image and see that there is a lack of function here and here and here and here and here. So again, don't smoke. Electrons travel around the nucleus in, again, structures called electron orbitals or electron shells. Atoms with vacancies in their outer shells tend to interact with other atoms. This is how bonds are formed. Bonds form through the interaction of electrons. And atoms tend to want to get rid of those vacancies. As a general rule, and they get and when they have 8 electrons, they're considered to be full. So they want to have 8 electrons. So if an atom has 3 in its outer shell, it wants to get rid of those, 1, 2, or 3. If it has 5, 6, or 7, then it wants to gather up more would be right, to make 8. So generally, when bonds form, they're going to form between one atom that wants to get rid of some electrons and another atom that wants to gather some up. And that's the way that bonds are going to form. We're going to talk about a couple of different types of bonds here in just a moment. So here's some electron shell models. Now, I said that outermost shell wants to have 8. There is one exception to that. Remember on day 1, I said always and every are bad words to use in a science class because virtually every time you use the word always and every, there's always and every going to be an exception. So in chemistry, with the shell model, the exception is the very first electron shell. The very first electron shell, which actually there are only 2 elements that only have 1 electron shell, and that is hydrogen and helium. Other than hydrogen and helium, all elements have at least 2 electron shells. Hydrogen and helium only have 1, and that first electron shell will hold a maximum of 2 electrons. Hydrogen has 1, helium has 2. When that outer shell, be it the one shell that only holds 2, or the other shells that hold 8, the outermost shell, whichever one is furthest from the nucleus, will want to be full at 8. So you have things like, again, hydrogen and helium. Hydrogen readily forms bonds. It only has 1 electron. It has 1 electron, so it either wants to get a hold of another one or get rid of that one. And it does that by forming bonds. Helium, on the other hand, has 2 outer shell electrons. It is stable at that point. Helium doesn't tend to form bonds. The video of the Hindenburg, the big blimp-like ship from Germany that was trying to land in New Jersey in the 1930s, I think it was, that blew up and burned on while it was trying to land. The Hindenburg was filled with hydrogen, a very volatile gas. The Goodyear blimp is not filled with hydrogen. It's filled with, if it's filled with anything, it's filled with helium. Helium will not explode. Hydrogen will explode. So, very volatile. Second electron shell, we see carbon, we see oxygen, and we see neon. Again, 4 outer shells electrons, so it wants to do something. It wants to bond, and we'll talk about that in a minute. 6 outer shell electrons, it wants to bond. All kinds of things will combine with water, with oxygen. You have all kinds of different compounds that have oxygen. You have all kinds of compounds that contain carbon. Neon has 8 outer shell electrons. Neon is stable. Neon doesn't form bonds readily. We go to things that have a 3rd electron shell. We have sodium. We have chlorine. Again, sodium, 1 outer shell electron, wants to get rid of it. Chlorine, 7 outer shell electrons, needs to get 1 more to be happy or to be satisfied or to be stable. And then argon, 8 outer shell electrons, again, a very stable compound. All of these elements that have a full outer shell, and there are several of them, they're what we refer to as the noble gases or the inert gases. They're gases that don't react. They're things like helium, argon, krypton, xenon, radon. there's one more that either has or has not been named on the periodic chart I have in this room. It's got a name on it, but I can't read it again. It's too small from here. But if you'll just remember all those ones that end in ON after helium, you got argon, krypton, xenon, radon. Those are all the inert gases. Bonds formed by the interplay of these electrons. This just happens to be a showing of how an ion, something called an ion, forms. All right, so what is an ion? An ion is a special type of atom that actually does have an electrical charge. And it has an electrical charge because through the action of a bond forming, an electron has either been gained or lost. So an ion is an atom, and again, I apologize, this is the only marker in here and it doesn't write very well. Atom with a charge. So if we have things these things are atoms that have either gained or lost an electron. The way you determine whether it's gained or lost is you look at its charge. When calcium, let's do chlorine, it's easier to remember. Chlorine, which is part of water, it's part of salt, sodium chloride. When chlorine forms ions, it gets a negative charge. When potassium, on the other hand, forms ions, it can actually get a positive charge. By the chlorine, I wrote a negative, just a single negative sign. By the potassium, I wrote +2. The number up there, if you don't see a number, it's an understood 1. If it's anything other than 1, you will see plus or minus that number. The number tells you how many electrons have been lost or gained. The charge tells you also whether it's been lost or gained. If you have a negative sign, and intuitively you're going to think if something lost, if it's a negative, that it means that's the one that lost. And no, that's not right. This is one of those times where intuition will steer you wrong. What we are talking about is the electrical charge. So to increase the negative electrical charge, that means you have to gather up more electrons. So if 2 electrons have moved or an item has gained 2 electrons, then it's going to be a -2, for instance. If it's lost 2 electrons, it's now going to have more positive charges, so it's going to be a +2. Make sense? Thank you. All right, so again, this is just a pictograph of what would happen. You see the sodium has a single electron, it loses it. It now has a charge of +1. The chlorine gains an electron, so now it has a -1 charge. Free radicals are solitary atoms that have unpaired electrons flying around. They have a very strong tendency to interact with other atoms. These different types of interactions make them dangerous to life. One of the things about the way our body works is we break things down. We take sodium and chlorine in a compound called salt, and we mix it together. See if one of these little markers will write a little bit better. Yeah, that's a little better. All right, so we take sodium and chlorine, and we mix them together or chemically combine them into a compound called salt. When that breaks apart, we get sodium just floating around in our system. They're not real healthy. The best thing to do is to bind these up in other products very quickly, and our body does that. Our body has a process to put them into places where they're not harming us. Free radical sodium ions. Sodium easily evicts its 1 unpaired electron to form, things like salt. The second shell becomes the outermost shell, thus no vacancy remains. That is a free radical, and you now have a sodium ion floating around. And those are actually beneficial to cells when they're in the right places. Atoms can fill those electrons by sharing, can fill those vacancies by sharing electrons. That is how chemical bonds are formed. A chemical bond is an attractive force that arises between two atoms when their electrons interact. A molecule of something is more than one atom. Now, it is very important that we understand the difference between a molecule and a compound. A molecule is a group of two or more atoms joined by a chemical bond. We have oxygen joined with another oxygen. That is what is referred to as molecular oxygen. Excuse me, my nose is itching terribly this morning. A compound, on the other hand, hydrogen, oxygen, hydrogen. So two oxygens combined together is a molecule. Two hydrogens and one oxygen combined together is a compound. So this is water, this is oxygen gas. So all compounds are molecules, are made up of molecules, but not necessarily all molecules are compounds. A compound must, by definition, have more than one element in them, or more than one type of atom. There is just another nice little picture graph of the water molecule showing the two hydrogens and the oxygen. Couple of different types of bonds. The first type is the ionic bond. Thing we really need to understand about ionic bonds is in an ionic bond, the electron actually moves. The electrons change place. These are strong mutual attractions formed between ions of opposite charge. And we don't use an equal sign in chemistry, we use an arrow. Sodium chloride. That is, and when you see an element of this type, there will be what is referred to as a polarity. That means that one side of that molecule is going to have a slightly positive charge, not enough to be considered an electrical charge, but it's going to be slightly positive. The other side is going to be slightly negative. And here's where that is shown. You see the sodium and the chlorine, and you see on the sodium side, if you can see this, there's three little positive charges to show you that this end is just slightly positive. This end down here is just slightly negative. And that is an ionic bond. The electrons are actually moving. A covalent bond, on the other hand, the electrons are being shared. I've got an electron, you've got an electron, I'm willing to let you have mine for a little while, you're willing to let me have yours for a little while. We are sharing that electron. That is a covalent bond. Unequal, and there's the nonpolar, where the sharing is equal. In other words, when the bond forms, if the shared electrons spend equal amounts of time here and here, that's a nonpolar bond. Does not have polarity. doesn't have that one end that's slightly positive and one end that's slightly negative. But if the pairing is, excuse me, unequal, or the sharing is unequal, then there is that separation of charges. One end is going to be slightly positive, the other end slightly negative. And a marvelous example of a polar covalent bond is the bond, that holds water molecules together. Water is a polar compound. And we'll talk in a few minutes about water and its unique characteristics. And part of its unique characteristics one of its unique characteristics is the fact that it has this particular type of bond form. Again, there are some covalent bonds just showing different mechanisms. You can see this is two hydrogen molecules, one representing the atomic number, and then this is the electron that goes with this one. This is the electron that goes with this one, and you see they're being shared in the middle. This is oxygen. This is molecular oxygen. You see, here's this oxygen has two electrons that can be shared. This oxygen has two that can be shared. And you see collectively they are sharing the four. And then this is a water molecule showing you this electron goes with the hydrogen, this electron goes with the oxygen, this electron with the oxygen, this one with the hydrogen, and you see they're being shared to form the polar covalent bond. Hydrogen bonds, the last type of bond, is actually kind of unique because hydrogen bonds don't actually form by the interplay of electrons. Hydrogen bonds actually form by the properties of positives and negatives. Hydrogen bonds form where one molecule that has a polar configuration and another molecule that has a polar configuration. And we know that this is slightly negative and this is slightly positive. And we know that positive and negative charges attract. And the bond that's holding this bonds, they appear in very large numbers. Big numbers when you see hydrogen bonds. There's always lots of them. And I think this next couple of slides will show us water. Again, hydrogen bonds between water molecules give water some of its unique characteristics. The capacity to dissolve things. The reason water molecules, see, this is slightly positive, and this is slightly positive, and this one's slightly negative, this one's slightly negative. The reason water is such a good solvent is it's got all of these unpaired charges. And when you dump something in it that is also polar, like salt, the negative side of the salt will be pulled by here, the positive side of the salt will be pulled by here, and this attraction is so great that the bond between the sodium and the chlorine can actually break. And when that bond breaks, this chlorine comes apart. Another interesting characteristic of water is cohesion. Water on the surface has quite a little bit of surface tension. If you've ever done a belly flop into the swimming pool, if you've ever just been in the swimming pool and slapped the water surface, you know that water has a lot of tension. If you hit your hand this way, you're not spreading that out over a lot of surface area because you can go through relatively easy. But if you turn your hand this way, more surface area, smack. If you've ever seen really divers that do the really deep, really high dives, you know, I haven't seen these in a long time, but when I was growing up, they used to have guys that would put a swimming pool, 12, 15-foot deep swimming pool, and guys would climb these things that looked kind of like radio towers. They would go 60, 70, 80, 90 feet in the air and then jump into the water. But when they did that, they always had this big bubble maker at the bottom of the pool. So right before they jumped, they would turn the bubble maker on so it would break up the surface tension and it wouldn't be so impactful on the diver. I told my group yesterday, and I'll tell you today, if you're ever trapped on a train trellis, that's the bridge on the train, and the train's coming and you can't outrun the train and you have to jump into the water and the water's 30 feet below you, unless you are a very expert diver and you know how deep that water is down there, don't go in head first. Go in feet first. And you want to go in as straight as you can. Because if you jump from 40 or 50 feet and you just happen to be going down like this, but you decide, how close is the water, and you look down just as you hit the water and your face hits the water, it can break your neck. So again, a lot of surface tension, and the less area you cover, the more that's going to be. You don't ever want to jump from 20 feet and do a belly flop, because that would, that's not good. Temperature stability. Water is very good at controlling temperature. How do human beings control our body temperature? One of the ways is we sweat. Swimming pools, if you go to the community pool or a country club pool or any kind of wild river country, wherever you happen to go, you know that when you get out there, it's way into June before that water gets really, really comfortable. You have to get in the water and you have to go in very slow, and your body has to acclimate because the water's so cold. Well, the reason the water is cold and the reason it takes so long into the summer for the water to get warm and get comfortable is, excuse me, that you have to allow for the temperature stability of water. It takes a lot of energy to raise the temperature of water. And lots of times in the early part of the summer, the first couple of weeks of June, even though it may get 85, 90 degrees in the day, it doesn't stay that temperature long enough during the day to raise the temperature of that water significantly. So, you start out with water that's 75 degrees. Well, after one day, it may have only gone up to 76 degrees. Whereas later on in the summer, when the days are longer and the temperatures are warmer, it warms up a little more. Great. Just froze.